Hello and welcome to another WJEC A level physics question. This is from Unit 1 in May 2009. It was question 5 and it's basically a question about electrons and drift velocity and such. First part of the question asks us to define electric current. So current is defined as the rate of flow of charge at A level. On the next part of the question, we're given the standard formula I equals NAVE, and we're asked to derive the formula given a clearly labelled diagram. So I've pre-drawn a diagram here where basically I've got a section of wire, and in that section of wire of cross-sectional area A and length L, there are some free electrons. These electrons are drifting with an average drift velocity v to the right, with a current of I flowing in the opposite direction. Remember that current is defined, or the direction of current is defined as the direction in which positive charges flow. An important part of this derivation is that the letter N stands for the number of free electrons per cubic meter. So I'm going to start by defining that. The key to this derivation is to work out an expression for charge, because current, as we've already defined, is rate of flow of charge. So the first thing that we're going to do is we're going to work out the volume of this particular sample, and the volume is the cross-sectional area times the length. Now inside that volume we're now going to work out how many free electrons there are. So if there are n free electrons in 1 meter cubed, there would be 2n free electrons in 2 meters cubed. So the total number of free electrons in Al meters cubed will be Al times little n. So do, on this type of question, explain what you're working out. So here I'm going to write down the total number of free electrons. It's going to be A times L times n. Now each one of those electrons has a charge of little e, 1.6 times 10 to minus 19 coulombs. So the next step is to say that the total charge, again a bit of writing explaining what we're doing, the total charge Q is going to be the total number of free electrons that we've got. Excuse this annoying pop-up. It's going to be the total number of free electrons that we've got, which is ALN, times the charge of each electron. Now in a time t, every electron in this particular sample of wire will have drifted from one end to the other. So let's make that clear. So time t is the time for all the electrons to leave the section. So now we can calculate, or we can write an expression for the current, the rate of flow of charge. Q was NALE, just slightly rearranging the letters from earlier, over T. But this term L over T is actually going to be the velocity of the electrons. If they travel a distance L in a time T, then their velocity is L over T. So we finish with that NAVE as required. There are other ways of explaining this, but that's a fairly simple way of doing so. For the next part of the question, we're asked to find the mean drift velocity in a wire of cross-sectional area 2 millimeters squared carrying a current of 3 amps, given that the free electron density, little n, is 5 times 10 to the 28 per meter cubed. So the rearrangement of the formula for V is I over NAE. I is clearly 3 amps. N is 5 times 10 to the 28 per meter cubed. Now the area is the bit where people go wrong. That area is millimeters squared, and a lot of people, as soon as they see milli, think that milli is 10 to the minus 3. But this isn't millimeters, this is millimeters squared. So we have to multiply by 10 to the minus 3 squared, which is 10 to the minus 6. Charge of the electron is 1.6 times 10 to the minus 19 coulombs. So substituting those numbers into the calculator, let's see what we get. And we end up with 1.88 times 10 to the minus 4 meters per second. which is a reasonable answer. Typically when we're calculating drift velocities, we're expecting answers of a millimetre per second or slower, and this is basically 0.188 millimetres per second. Next part of the question, we've got two copper wires P and Q connected in series, with P having double the cross-sectional area of Q. A battery is connected between the ends, and we've got to complete the following sentences. The current in Q is the same as the current in P. These two pieces of copper are connected in series, and we know from basic electricity work that components in series have the same current through them. For the last part of the question, we're asked about the electron drift velocity. Well, in the equation that we've used in the previous part of the question, we can see that because the current is the same for both parts of the wire, N is the same for copper, they're both copper, and N is a constant for copper, and E is constant, we can actually see that V is inversely proportional to A. So the smaller area has the higher velocity, and because the section Q has got half the cross-sectional area for P, that means that the velocity of the electrons in P is going to be half as much as the velocity of the electrons in Q. Once again, thank you for listening. Please remember to like and subscribe.